and welcome to the show. This is the last and final episode of the Learn It, Turn It, Burn It, Torque and Drag miniseries. And today, if you can't tell, today is brought to you by Volant. Look at it. I've got the real deal in my hands. This is the coolest thing ever, right? It's not very often that I get to actually handle things that go to the on rig sites. Most time people tell me, don't touch stuff, you're gonna break it. This one, if I break it, well, it's okay. I doubt that I'm actually gonna be able to break this pretty sturdy piece of equipment here. If anything, I'll probably end up breaking my keyboard because I'm gonna drop it in my mouse or even bust up my monitor. But yeah, usually I don't get to actually touch things at the rig. So this is pretty cool. A lot, hooking us up with some of their equipment. Right. Yeah, today's brought to you by Volant. Thanks, you guys. All right, we'll start kind of getting on with the show, and I'm going to be gentle in setting that down. No pinch points or break any fingers or anything. Yeah, I don't have to start filling out JSAs to be able to do live streams. That would probably be counterproductive for my world. All right, guys, this is episode number 8, and we get to finally book in this thing with Brandon Foster. Before he comes on screen, I want to be able to tell him my undying appreciation for him and what he has helped not only myself do and be able to put together these 8 episodes, but he was a crucial part in being able to make this whole thing come together. And so it's not just for me, it's for the entire industry. One of the very first times I ever heard Brandon speak was at an IEDD event probably 5 to 6 years ago. And his passion for wanting drilling engineers to actually be drilling engineers and not just paper jockeys was undeniable. And it was like as soon as he got done with his presentation and we went to lunch, the first thing I did was just go find him, just go run down, find him, shake his hand and say, man, I absolutely loved everything you had to say. And I have been a huge fan of his ever since. Had I had a Sharpie and a white t-shirt on at that point in time, I probably would have asked him to sign my shirt. That big of a fan, and so happy to be able to have him back on to be able to wrap up the Torque and Drag miniseries and to answer your questions and to be able to wrap up a couple other things. He's put together a couple little things here. So he's still got a full-blown presentation to be able to share with you guys. So it's going to be absolutely amazing. So do me a favor, tag someone in the comments who you think should be learning more about Torque and Drag. Tag somebody in the comments who you think already knows everything about Torque and Drag, or just tag somebody in the comment section just to tag them so they can come back and watch this later. All of it's a huge help. Let us know where you're watching from. Let us know which episode was your favorite so far. Which one did you learn the most from? I know there's probably a handful of people in the comment section right now who have watched all of these episodes. And once again, today is brought to you by what? See, there we go. Okay. Yeah, it's not solid on the inside. It's heavy like it is. It's not. All right, let's go ahead and say hi to a couple of people. So we've got Soren that's tuning in from Denmark. Soren's been here for a handful of episodes. Thank you for being here. John DeWart, as always, tuning in. It's like clockwork by this point in time. Alex, tuning in from Oklahoma City. Thanks for being here. David Dill, thank you, sir. Zwar, tuning in from Houston. Zaid says, hi, everyone. Turn and burn, baby, says R.D. Morrison. Yes, sir. We got tuning in from the Kingdom of Saudi Arabia. George says, in the urban sprawl of Houston. Yes, it's a very large urban sprawl there. Akabri? I just butcher names. I'm sorry, you guys. I do really apologize. I wish I could pronounce everybody's names right, but can't go through them this quick and be able to get it done. Soren's here. Roy, this guy's been asking all the questions. So, Roy, thank you so much for being here and being continually tuning in and asking questions. I really do appreciate it. Mr. Fans here from China. Thanks for being here. He's also been asking questions. It's probably like between the two of those guys, it's probably 1 and 2 on who asks the most questions. That and maybe Randy Soto. I don't know if Randy's here yet. Omar Rashid tuning in from Boston. Right. Boston's starting to become a regular place. Mr. Alabi tuning in. Gabriel, says hi from Mexico. Tommy Haley tuning in from Willis, Texas. And Mr. Ian Purge, thanks for being here. did that go? Oh, wow. Oh, wow. There's a lot more comments. Okay. Mr. Lee from Vietnam, Houston, Venezuela. Juliana tuning in this morning. Thanks for being here. Ari tuning in from Dubai. Peter Cho says, hi, all. Mr. Robert Carrington and the guys over at Vibration Technologies. Thanks for being here. Peter Cho says Susan Saeed from Iran Energy. Donna. Sir Michael Phelps tuning in from Abu Dhabi. Mason. Maysam. Tuning in. Says, hi, everyone. There we go. Yeah, get David Briones in here. He needs to learn something. Thanks for making some tags in here. Alfredo tuning in from Woodlands, Texas. Is it Rivas tuning in? Says, hi, good morning. LinkedIn user from the Rockies. All right. Calgary. Hello, everyone. My buddy Barry Lacoste. He's here. Ian from Uganda. Ali from KSA. Thanks for being here. Simon says, good morning from the Woodlands. And then once again, Simon says, hello. I need to hook up on those. I'm guessing it's not grains, it's the frames. And these are custom painted Cerakote, the stuff that they do for a lot of firearms and stuff. And Mr. Dean tuned in from Alberta, Canada. And guess where he works? He works over at Volant. Dean's actually been on the show before. Not the Torque and Drag miniseries, but on the Vidor Locksmith show. He's been on the show before. So special thanks to the guys over there at Volant for making this today happen. Yep. See, Martin said frames. Martin's a good buddy of mine. He's a good guy. Worked out on the rig with him. Actually, he was working. I was just there. So I shouldn't say I was working with him. I was just out of the rig. Good morning, everybody, says Terry. And then Adrian says hello from Houston. All right. Let's get this show rolling. Once again, today is brought to you by Volant, and I have a little special. Oh, wait, hold on. Order of operations here. Got to put the bit on it before you go on whole, right? If you guys would like to win a drill bit, this is the final one to give away during the Torque and Drag miniseries. So this is the easiest way to be able to get your hands on one of these giant drill bits. We've already sent a couple of these out. I think our very first one was Dane Greaser. Then David Thiel. I think Luther 1-1. George. I can't remember all the winners. Been giving away a lot of stuff lately. So hashtag Volant. Right? This is a full-size, real-life. These are real threads, right? These are API threads. Don't do NDT testing on them, right? But actually, it might be kind of fun if we did do NDT testing on a 3D printed drill bit. That might actually be kind of fun, right? If you want to win yourself a drill bit, hashtag Volant into the comment section right now. And I'm going to read you all a little thing about see if I can make sure you got the. I'll hold it like a baby. There we go. So here we go. Maintain your casing string and well integrity while drilling, reaming, and completing while completing critical, challenging, high-profile wells with Volant's hydroform crimped centralizers. Case in point. Whoa, I almost dropped that. Crimped centralizers provide a reliable mechanism for leaving friction when the available slack-off weight at surface is not enough to allow the pipe to run and hold. By fixing the centralizers directly to the casing string, a device widely used for casing standoff is turned into a powerful solution for managing axial friction and improving the reliability of ERD casing running operations. Combined with Volant Red software, your casing run can be modeled and monitored to predict running loads and improve the efficiency and effectiveness of your runs. Recover your hook load and reduce run times in ERD wells with Volant's suite of digital and hardware solutions. Visit volantproducts.ca for more information. This is like getting it right. You know, when like the people have to like drink out of the beverage cup, right? You got to get the logo just there. Granted, you don't drink out of it because it's got a hole in the middle. But special thanks to Volant. Hashtag Volant if you guys want to be able to win the drill bit. So let's give away a drill bit. All right, now I'm going to actually set this thing out of the way because I'm going to be too tempted to keep playing with it because it's actually pretty cool. I would juggle it if I actually could juggle. He says, bravo, David. Yeah. Oh, slightly nervous. I'm trying to be able to get that right. All right. See, we've gotten all of the, hashtag Volant. And actually, guys, do me a huge favor. Go to the volantproducts.ca website. Go over to their website just once today. Let's give them a little spike in traffic over there. Just check out their website. Go over there, take a look. Maybe buy 2 or 3 of them. Put them in your cart. Send them to your house. Not sure that's how you purchase them, but hey. I've lost my little button here. Okay, back to brand. There we go. Let me add this to the stream. Where is it? All right, 50. Let's see who the winner is for today's Volant sponsored drill bit. And Naufel Riahi. You are the winner of today's Gibson Reports full-size directional drill bit. I know we're already connected on LinkedIn. Please, sir, send me a message with your contact information and details, and we will get that drill bit sent off to you. All right, on with the show, and special thanks to Volant once again. Do appreciate it. Here he is, the man of the day, man of the hour, man of the past 8 weeks, Mr. Brandon Foster. Thank you so much for being here, sir.
Sorry. Hey, you're too kind. Thank you, David. It's good to be here. This has been a great series. This was a great idea, and thank you for putting it all together. It's a lot of work, and the attendees that learned anything should be sending you a thank you.
I mean, yeah. You send me a little thank you, maybe a little. You can send me some other little Volant. Give me this little stress
ball. That's cool.
But it's in the shape of their little centralizer thing. I thought that was pretty cool. Yeah,
very cool.
So yeah, if you guys want to send me some swag, whatever it is, I'll be more than happy to take it off your hands and probably just throw it in with some of the winner stuff and keep sending it around the world. So, Brandon, let me ask you this. What have you learned from the prior episodes?
Man, it's been really great. There's things that I had forgotten about that I was well reminded of. Some of the disconnect between academia and industry and getting our terminology right. It's been really great. I've picked up something from each of the presenters, and it was really great to see what they all had to contribute.
Yeah, what is it? There's academia, and then there's practitioners. As somebody who I follow in the fitness business says, it's like, well, once academia has written a PhD paper on it, or somebody's written a technical paper on it, that means somebody else has already been doing it for a while.
Right.
So, all right. I know you have a presentation for us today to be able to share. Do we want to go ahead and cue that one up?
We sure can. Unless, yeah. What did you learn? What stuck out to you over the course of 7 episodes?
That I now know how much I don't know about torque and drag.
It's a big subject.
It is.
I remember one of our first conversations, like, yeah, what would you put in a torque and drag presentation? Like, oh man, that's not just one. There's so much. And really, we've just scratched the surface. There's lots of other ways that you could look at it. Whether we haven't talked about things like stuck pipe and survey corrections, and there's lots of little details hidden in the physics of torque and drag.
And seeing, I'm not allowed to comment on these as I found out the other day. But I will say this: there are a lot of SPE abstract papers that have been submitted for this year's ATCE that even further and change and kind of push the envelope of torque and drag.
Interesting.
And not that I am the expert on being able to say whether they are right or wrong, But there are many people that are looking at torque and drag and how to be able to solve that in a multitude of fashions. So I know there's been a lot of debate, the soft string versus stiff string modeling. Some of these other methodologies that were presented in the abstracts, add even more to that, to even more options. And so I think the other big thing that I've learned is that there are no rules of thumb, right? It is like, let's look at the scenario of what we're doing. What is our goal? What are we trying to accomplish? What is the length of the well? What is our wellbore profile, hull sizes, all of that? What are we actually trying to be able to achieve here? And then, then do your torque and drag, then do your modeling. And then, being able to circle back and see what actually happened versus what had you planned to be able to better understand going forward into the future ones. So
where's ACTE this year? That might be one worth attending.
It will be in San Antonio.
Not terrible.
I will be moderating a session. We are working on the name of that session currently. And it will be very, very interesting. I will say this, though. I had to trade off my favorite paper to another group. There's multiple people involved here, so I didn't get to, just cry about it and go, I want to have that one on our group.
Hopefully the sessions aren't at the same time.
I hope not. Okay, I will say this. There are 2 papers that I saw come through as abstracts, and I am ecstatic just to be able to hear the stories that come along with them, right?
You may have just sold me.
Once they are out there, I promise you, it's just like, man, I'll as soon as we're allowed to say, I think it might be early to mid-March, I'll tell you what the titles of the papers were, and or at least if we can share the abstracts or something, then I'll give you a little snippet, the ones that I think are going to be really interesting.
Cool.
There's a lot of the typical stuff that's just kind of like, yeah,
that happens. Yep.
Yeah.
Got to have filler.
Yeah. Another stuck pipe thing. Well, okay. But then again, I can still learn a lot about stuck pipe. So I'm not beyond that. So, all right. Brennan, go ahead and share your presentation. We'll get that one loaded up here. As per normal, guys, if you have any questions as we are going through, please ask the questions. We'll start to star everything, put it in there into the our little registry on here. And as soon as Brandon finishes up, we'll be giving you we'll be firing off all of those questions to him. So this is your last and final chance to be able to have some free Q&A consulting time with Brandon Foster. Because after this, it's probably not going to be free. So, all right, here we go. Brandon, I will turn it over to you, sir.
Okay. Oh, that's the wrong one.
Introduction to torque.
That's the
drag.
first one we
did.
I sent you the wrong one. Hold on.
No worries.
My gosh.
Yeah, while we're waiting. Volant, thank you so much for sponsoring episode number 8. And, obviously New Park, as you can see there, did episode number 1.
Sorry, Volant. Love your centralizers. That wasn't intentional.
Yes. So, if you're a big fan of Volant, you can get one of these, or you can get the real centralizer thing to put down your hole. See, less stress both directions. Less stress on your well, right? Because you've got Volant products down hole, and less stress at your desk because you got the little stress ball squeezy toy. I don't know. This one might actually help if you're a rock climber or something. The amount of gonna give it a good one there. All right, guys. While we're waiting here, let us know what was the biggest thing that you learned while watching the Torque and Drag mini series. Which episode was your favorite, and what was the most important thing you learned? Data without a model isn't science.
Bingo. It's just
somebody
drugs.
Somebody watched episode number 1.
Fantastic. I think we're good to go.
Zora says, "Morning, Brandon and David. Thanks for these sessions." You're more than welcome. Travis Bowden says, "Good morning, David." And Amit says, "Hi, everyone." All right. There we go. We are off and running. Take it away, sir.
Fantastic. Thank you. Sorry about that. Yeah, so a quick little recap of what we already saw. And there was 2 questions that came up during some of the presentations, and or people had messaged me afterwards asking about it. So I thought we should cover it. One was real versus effective tension. And the other one was from Divine Samieri. And he had asked during one of the, I think it was actually during episode 1. And then he messaged me last week and reminded us that we hadn't really covered this yet. So I worked up a little practical exercise to address how you figure out what you set your maximum hook load and your maximum torque to if you were drilling a particular well. And then we can do your Q&A if there's still any stones that we've left unturned. This slide, if you download this presentation, it's got hyperlinks to all the presenters, all the slides, and all the videos that have been uploaded to the World Wide Web. There's still a couple that we're waiting for from Mitch and Devi. But once we get those, then those hyperlinks will be updated, and then you can use this kind of as a navigation portal to be able to get to everything that you would need in the future. Just to back up, David had asked, what did you learn? There's so much material that we covered. I thought that it was great that we had a mix of some PhD folks. Stefan and Dr. C covered a lot of theory and some really interesting application of that theory. I liked how Trolls kind of unearthed the stuff that you don't normally think of with torque and drag. We're typically looking at what's your surface hook load, what's your surface torque, and that's where a lot of us stop in terms of understanding what the output is from the software. But Trolls really showed us that there's so much other things that you could be looking at: side forces, bending, stretch and twist, and those are pretty interesting if you kind of get creative with what you can do with the output. I mentioned earlier when David and I were talking survey corrections, with stretch and twist, you can figure out what your true drill string length is. And we don't normally do that. I know of one directional company that actually accounts for the true drill string length, but most of the time we don't. We just take the tally as being the correct drill string length, and it's not. Anyway, I think that's an interesting point. Neil did a great job of just the practicality of, what are some of the little pitfalls when you're running the software that could cause you to have, incorrect interpretation or results, and just using the model in real time or even in the planning mode. I thought that was a really great presentation. Mitch did a great job talking us through some of the techniques that you use with swivels and reaming and floating, and there's a lot of sophisticated techniques as the wells get longer and longer and longer that you have to employ to be able to get pipe down. And I thought Mitch did a great job of covering that. And then, of course, here just last week, Devi talked us through real time, and that's the fun part, when you actually drill in the well and as an engineer able to use some of the models to be able to make better decisions as you drill in the well, save your company money, save your company time. So yeah, I thought everybody that presented just did a fantastic job, and really appreciative of them contributing their time and thoughts to this effort. Okay, so one of the questions that came up is, what is true tension versus effective tension? And there is a great SPE paper, I've noted it here, 1747-85, if you want, that goes into greater detail than kind of what we can do here. But there's a deck of slides that comes with the paper, so that's helpful as well. But basically, effective tension is what we're interested in and concerned about when it comes to running a torque and drag calculation, understanding whether or not buckling is likely to happen to our drill string or our casing string. And to a certain extent, it's all you really need to be worried too much about from a drill string stress standpoint. Now, with that said, when you do a von Mises or VME calculation, and we're going to talk about that a little bit more later. But when you do VME, you're using true tension, and true tension. If you think about like a submerged drill string, there's several examples here. Look at the middle one where you've got a joint of pipe submerged in fluid, and this dotted line is meant to represent the true tension in the string. And this vertical part of this triangle is the neutral point. So the lower part of this string, when it's submerged in fluid, is in true compression. So if you kind of take that to the logical end, if you say, okay, if the deeper I submerge pipe, the more compression there is, then surely there's a point where the buoyant forces of being submerged in a fluid buckle the pipe. That's not true. There's an infinite, you could run an infinite amount of pipe into the ocean and it wouldn't buckle, provided you don't hit the bottom of the ocean floor. Because the buoyant forces also provide an equal and offsetting stabilizing force. And that's what this extra little term is that we add and subtract from the true tension. So PIAI is internal pressure and internal surface area if you're talking about a tube. And the PEAE is external pressure and external cross-sectional area. So your pressures are going to be the same if it's open-ended. If you're submerging this pipe in fluid, it's a function of your hydrostatic pressure, but the areas are a little bit larger on the outside, a little bit smaller on the inside. And that stabilizing force of external pressure offsets the buoyant force that's pushing up on this pipe. And so your effective tension, this black solid line, is always zero at the bottom of the pipe if you're looking at effective tension from buoyant or pressure forces. And so there's 5 different scenarios here. Just, pipe in air, pipe with fluid on the inside, pipe with fluid on the outside, putting pressure on the inside of pipe, putting pressure on the outside of the pipe. And in all of these cases, you're able to stabilize the pipe regardless of what the true tension may be. It might be higher, it might be lower than effective tension, or it might be the same as effective tension, but it acts as a stabilizing effect. And that's why when we run torque and drag, we tend to not look or worry ourselves too much about true tension and just focus on effective tension. It's important because it's the starting point of the calculation, but really buoyancy cancels itself out with the stabilizing effects of this whole term. If you had a strain gauge in the string, what you would read is true tension. So that's something that we have to compensate for when we run like downhole weight and torque subs. But that's not that doesn't mean that effective tension isn't real. And that's an unfortunate side effect of some of the things that have gone on in industry. There's been papers written where they call this, imaginary forces, that effective tension is imaginary. It's not imaginary. It's a very real phenomenon. In fact, in laboratory experiments, they've duplicated that this is real, where they take cylindrical solid bars and they put it in a pressure chamber, and there's no tensile or compressive loads on either end of the bar. All they do in the experiment is put pressure in the annulus, so to speak, of this bar that's floating in seals. And when you pressure up the inside of the chamber, it puts the pipe in effective tension, but there's no true tension because you're not pulling on the bar. And sure enough, you can part the bar at the rated tensile capacity of the bar. And that's actually, they discuss it in this paper here. It's called the Bridgman paradox. It's a very real force. You're not imagining that this thing is breaking. So that's one of those areas where I don't like the terminology that we use sometimes in the academic world, because us mere plebs that are reading these papers, you're like, what? How? I don't understand if it's an imaginary force, how it could actually break stuff, but it does. It's real. We shouldn't call it imaginary. So hopefully that hasn't confused you more than you already are about effective versus real tension. Read the paper if it's still a little confusing, but these Norwegian guys did a great job of kind of walking through what is effective versus true tension. The other question that we had, and my graphic is kind of covering this up here. That's one of the problems with StreamYard, as it kind of manipulates your text. But Divine asks, what is the maximum allowable tension, maximum allowable torque at surface? How do you calculate that? Well, there's a whole who, what, when, where, why aspect to answering that. It's a lot more complicated question to answer than what it sounds like. So when I say who, are we talking to a drilling engineer? Are we talking to the company man? Or are you talking to your grandmother? There's different levels of complexity that you can go to into determining what's the maximum tension and torque that you can apply at surface, right? So this discussion is going to be more on the engineer side, not on the grandma side. My grandma's never asked me that, but if you've got a grandma that's really interested in oil and gas drilling, you may want to dumb it down a little. What is your limiting factor? Are we limited by the drill pipe? Are we limited by something in the BHA, or perhaps some tool that's in the string? From a torque standpoint, or even from a tension standpoint, are we limited by rig equipment? Is it, are you at risk of pulling the derrick over from overpull standpoint? That you have to look at the whole system and all the different components of what the tension limits are to really arrive at that number. What I tend to find is what really limits our maximum tension and torque is our emotional state at the time you ask the question. And what I mean by that is, in the planning phase, everybody tends to be really happy to have big safety margins. Like, oh, we're not going to pull more than 80% of, any of our equipment or any of our pipe. But then the minute you get stuck, okay, let's pull to 100%. I mean, so we're very willing to compromise our morals if it means that it'll get us out of a bind. So I think we need to be realistic about what we're legitimately, as a team, willing to do in terms of pulling and turning on our equipment, and then not change just because we're stuck. When this question comes up, it seems like it's always at like 4 o'clock on Friday, you get the urgent phone call, can you run, these numbers real quick for us? Or it's in the middle of the night. It's never, middle of the afternoon on a Tuesday. It's always urgent, and it's always at an inconvenient time, unfortunately. So it's good to have all this worked out in advance so that you don't get those midnight phone calls. And I can't even remember what I wrote here because of my graphic. Where, assuming that, if we have a weak point in the string, where is it currently located? So, like, let's say that we had, I don't know, let's just pick on agitator. Let's say we've got an agitator in the string that has less makeup torque than the rest of the drill pipe that we have in the hole. Well, the max torque that we can apply at surface depends what the bit depth is, because the bit depth impacts where that agitator happens to be in the wellbore at any given point in time. So your maximum tension or torque, if it's governed by some weak component, is going to change as you drill the well. So I like to graph it out and give the driller a map of, okay, this is the maximum that you can see at surface at any given bit depth, so that we don't overload whatever our weak component in the string happens to be. And then the why, I think, is maybe more important than who, what, when, and where. What I mean by why is, why do we accept a given limitation as just statement of fact? All too often, we design our well bore, we get ready to go drill the well. At the last minute, we run the calculations, and then we try to solve all the problems. Well, really, we need to be working all this out before you pick casing sizes, before you pick casing points, before you pick what drill pipe you're going to rent, so that you've solved the problems before they become a problem. And that's not usually the way we do things. We do it too late in the process to actually affect big change. And this exercise that we're going to go through, I think, illustrates that exact point. So here's our our example. This is a real well that I'm working on, that we're going to drill this summer. It's going to be not a crazy well. I mean, we're looking at 26,000 foot measured depth, 16,000 foot TVD. It's pretty deep. It's deeper than most wells in this state from a TVD standpoint. There are other 3-mile horizontals being drilled. And so people and a lot of service providers have a lot of confidence when they just take a glance at this trajectory, like, oh yeah, we can do that. We've been drilling 3-mile laterals for XYZ company just north of you, for the last 3 years. This is no big deal. And so we'll actually do some engineering and figure out if that's true. Not huge step out, 1,500-foot step out, 2-mile lateral, real gentle nudge up here, 1.5 degrees per 100, building on eighths, so not aggressive build rates or dog legs anywhere. It's a 4-string design, so we've got 13 3/8 surface casing to cover up our freshwater. And historically, in this field, there's never been any horizontal wells drilled, but historically, old 8 set at around 7,000 feet, and then they would set production casing across the reservoir down here, and it was usually a long string of 5.5. Well, because we're going horizontally, and because we need different mud weight in the lateral than what is needed in the shales just above the lateral, we need another string of pipe to isolate these shales from what we do in the lateral. So there has to be a string of casing here close to the reservoir entry point. So to drill a normal, 6-inch or 6 1/8 inch hole, we need 7-inch casing. Well, that's a long 7-inch string of casing, but that's what was originally planned before I picked up the project. So that's what our wellbore looks like. It's a hard abrasive sandstone that's going to take almost a month to drill that lateral. And then there's a big, very high pressure frac, multi-stage frac that's planned after you get the drilling done. And the comment was made, this is just like a Bakken well, but deeper. Well, Bakken wells are 10, 11,000 foot TVD. We're adding an extra mile of TVD to the well, and that has some pretty significant implications on drill string and casing design. So let's take a little look at figuring out maximum tension and torque. So we're just going to focus for now on the production hole section. So drilling that horizontal. The rig doesn't come with 4-inch drill pipes, so we're going to rent 4-inch S135 XT39, pretty common for U.S. land. That's what most of the rental companies are going to have. And if you were going to base it just off of the spec sheet, you'd ask your rental company, send me a spec sheet for the pipe we've got. And most of them are not going to send you a new drill string. It's going to be rated to API premium class or better. So what premium class means is there's 80% of the nominal original new body wall remaining. When they run the inspection, when they do full length ultrasonic on the tube, they'll reject any joints that are less than 80% of the original wall thickness. So all we know for sure when we rent this pipe on day one is that the most worn pipe could be as much as 80% or 20% of the wall thickness worn. So the rating for that, for API premium class, you can see over here in the spec sheet, is almost 33,000 foot-pounds in torsion and a little over 400,000 pounds of tension. But you don't normally operate right up to that premium class rating. We like to apply a safety factor or design factor. And it's pretty typical to say 80%, which is 1.25 design factor. So you divide all the ratings by 1.25, or you multiply by 0.8, depending on, which one makes more sense to you. I've tried to reference both design factor ratios and percentages here. So that brings our maximum capacity down to about 320,000 pounds tension, or 26,000 foot-pounds for the tube. That tube limitation shouldn't be a problem, because our maximum makeup torque is 22,000 foot-pounds. And with makeup torque, we tend to be a little bit more aggressive. We tend not to just knock 80%, derate it by 80%. A lot of operators will go up to 90% of makeup, or on ERD wells, it's not uncommon to go to 100% of makeup. There's nothing that says that you can't go to 100% if your top drive, if the torque measurements that you're measuring are accurate. You won't have downhole makeup all the way up to 100% of makeup. If you haven't calibrated your top drive in a while, then you probably do want to put some design factor or safety factor on it. But what we're going to do for this exercise is just assume that we don't want to go more than 90%, which is what's called 20,000 foot-pounds. So right now, our limiting factor, 20,000 foot-pounds for torque, and the maximum tension that we can apply at surface is 320,000. So you'd add your block weight to that 320,000. That would be what 90% of us will do when we're determining maximum hook load and maximum torque, assuming this is a mono diameter drill string that's all the same pipe from the BHA to surface. That's kind of stage one of determining tension and torque limits. Now, stage two, you break out your old torque and drag software and you run some calculations. And so we're going to calculate all these graphs are going to show the same thing. On the left, it's our effective tension. So you can see my x-axis is 100,000 pounds of compression. 0 is neutral, so there's no tension or compression here at 0. And then as you move to the right, this is all increasing tension from 0 to 600,000 pounds of tension. And the colored curves, that grouping is the calculated tension for a variety of friction factors from a 0.1 to 0.3. And the black dashed line is 100% of premium class rating. So that 400,000 pounds that we got from the spec sheet. And then if I derate it with my 1.25 design factor or my 80%, then that puts the maximum line here in this gray dashed area. So it looks like when we run the simulation for moderate friction factors of, kind of somewhere here in the middle, 0.2, we'll be okay. We're just under that 80% number. And we've got a little bit of margin for overpull. Now, if we happen to have high friction, then we're over that tension limit, but we're close. This would not make me sleep very good at night. We don't have much margin here. It's going to be pretty tight. But theoretically on paper, it's doable. If you look at the torque, so the off bottom torque on the right, we've got 0 bit torque when we're off bottom. And torque grows as we move up the drill string. There's a little bit of extra torque in that shallow nudge because this is a deep TVD well, and there's a lot of tension across those shallow dog legs, like Trolls was talking about. And you'll see that our predicted surface torque is well below our 90% makeup limit and our 80% tube limit. So there shouldn't really be a problem here with torque. There might be a little bit of a problem with tension, but on paper, it should be doable. Now, the problem with this simulation is this is all assuming a smooth well path. There's no real dog legs or tortuosity added to the well. So we need to take that into account. So what I've done here is it's the exact same calculation, but we've induced artificial tortuosity based on offset wells. So this isn't just, Brandon's random number generator. This is taking an offset as drilled well and coming up with tortuosity factors that replicate the sort of tortuosity that you have when you drill in this area. And it's nothing crazy. If anybody's interested, I can send you, what I came up with, but we're talking about a degree and a half, 2 degrees more than the theoretical plan at any given point in terms of dog legs. So it's very gentle in terms of tortuosity. You're not going to do a lot better than this. And you'll notice now that same 0.2 friction factor that was probably okay but questionable is now going to be over the limit for tension. It's still okay on torque. So for torque, I'm expecting not to have more than around 15,000 foot-pounds of surface torque. So I've got 5,000 foot-pounds of margin. Torque should be okay. Tension might have a little bit of a problem. If you plan to just drill this well and not pull out of it, everything's fine. So if that's all it takes to get your paycheck is drill and not trip, then mission accomplished. One of the mitigations that people sometimes look at is, okay, well, I'll just plan to back ream. If I back ream out of the hole, then my tension drops very close to this green line. That's our rotating off bottom or ROB line. And I've even been guilty of this in the past, saying, okay, well, we'll just back ream to manage tension. And we'll see in a minute why that might not be such a great strategy. Okay, so that's where we're at. We may have a tension. We do have a tension problem. Right now, we do not have a torque problem. The next little level that we need to look at here, and this will look much better when you download the slides. It's getting distorted, is to look at combined loading. So this sometimes is referred to as combined loading or triaxial stress or VME stress. VME stands for von Mises equivalent stress, and it is a way of looking at all the different sources of stress on your pipe. We pull on the pipe, that's the tension or compression. We bend the pipe around dog legs, that adds additional effective tension. We've got radial stresses and hoop stresses due to internal and external pressures. And then we also have shear stresses. And one of our big shear stresses when we drill these wells is torsion. So this term over here, that's torque. So you sum all these things up and you take the square root, and that value is in units of PSI. And you compare that effective stress in PSI to the yield strength of your material. And you've probably seen this before, the output of this on casing design software. The big ellipse is your VME ellipse. That's calculated from the yield strength of material. And the goal in casing design is to make sure that all your design loads stay inside the ellipse. The other place you may have seen this is on the drill pipe spec sheet. This graph on the right is the tube combined load limit, where we cross plot torque on the x-axis and tension on the y-axis. So earlier when we said that that 4-inch drill pipe was rated to 400,000 pounds, that's only when there's no other sources of stress. Well, as I said, a big source of stress is torque. If I've got no torque, I can pull to 400,000, but as soon as I put torque on the string, then I can't pull as much. So if I had 30,000 foot-pounds of torque, now I can only pull 250,000 pounds of tension. That is a very important factor, especially on deep TVD wells. And here's how it manifests itself for this example. So I've got my artificial tortuosity. I'm no longer looking at just uniaxial limits. I'm going to look at VME limits. So I've got my loads have not changed. The color curves are the same, but now my gray shaded area, my black shaded area, those are taking into account hoop stress, radial stress, torsional stress, bending stress. And now my uniaxial limit is optimistic. Anywhere where there's a dog leg, you'll notice that my tensile capacity goes down, and I'm even now more over the capacity of the pipe when I go to pull out. And it turns out that my tube is at greater risk of being overstressed than my tool joint. Previously, the 20,000 foot-pound limit that I had on my tool joint was my limiting factor. Well, because this is such a deep TVD well, it's actually the tube that limits my torque. I can't say to the rig crew, yeah, go all the way up to 20,000. That's 90% of makeup. No, actually 17,000, 18,000 is my limit before I overdo it on combined loading or VME. Yikes. Okay, well, that doesn't leave me hardly any margin at all. It certainly doesn't leave me margin for drill bit torque when I go to put the bit on bottom. So this is not shaping up to be all that pleasant of a well to drill. I mentioned earlier, well, we'll just back ream out. Well, this is what it looks like if we back ream. You'll notice that the tension collapses. I don't have this wide spectrum of tension when I'm back reaming. It's over the limit, and it's even more over the limit now on torque. If we said that 0.2 was our most likely friction factor, my combined loading, if I just toggle back and forth between these two, notice how that combined loading, it's in gold now, just to remind myself that this is a back reaming load case, not a just rotating off bottom load case. So here's rotating off bottom, here's back reaming. It's really ugly. In fact, I'm going to well exceed the capability of the pipe if I try to back ream. So we've got a real problem here. This is not going to be good. One solution would be to run heavier wall thickness pipe on the top. So most rental companies are going to have 14-pound S135. And we do a little asking around and digging, and there's one vendor that's got some 15.7-pound drill pipe. And 15.7-pound, because it's got heavier wall thickness, it's got a little bit more capacity. At least I don't have this massive torque problem that I had before. The tool joint now is still the limiting factor, but man, it doesn't look good trying to pull out of the hole. So yeah, this is a little better, but it doesn't really solve my problem. Another scenario would be to take a page out of the deep water playbook. So in deep water, it's very common for our drill pipe to be inspected to a higher level than API premium class. So what we can do is specify 90% remaining body wall, RBW. And what that means is when that drill pipe comes back from rental, if it's going to go out on a new job, when they do a full length scan of the tube, anything that has more than 10% of wall thickness loss gets thrown in the coal pile. And we only keep the stuff that's got 90% or more remaining wall thickness. And so this looks pretty good. The problem with that is you're going to pay more for rental, and you're also going to pay more for damages, because as you drill this well for 30 days in an abrasive sandstone, there's going to be wear on the tube. And now you're probably buying a lot of drill pipe if you're going to drill with this high spec standard. Gulf of Mexico, generally not that abrasive. That's an application where, you know, this is doesn't have massive financial consequences. And if you just look at the scale of things, spending $1 million a day versus $100,000 a day, it doesn't really hurt us the same way financially in an extremely expensive water well as it would in a U.S. land well if you have to buy a drill string. Okay, so that's a lot of our who, what, when, where. Now, the why, just accepting our well design as statement of fact is the real point that I wanted to make here. You go back to the drawing board and you say, hey, why are we setting where we're setting? The 7,000 feet kind of seems wasteful. And here's why I say that. The mud weight on all the offsets from surface casing all the way down to the reservoir is all the same. There's no pressure transition in here that requires us to set a string of casing at 7,000 feet. Now, back in the day, 40 years ago, when these wells were drilled, they were all drilled with water-based mud, and there was reactive clays in this interval. And it appears, just from reading offset drilling reports, the reason why they were setting casing was because they were running out of time before all these shales would hydrate and eventually fall apart on them. So they'd set casing at 7,000 feet to buy themselves more time to get to the reservoir. These wells were taking 60 days to get drilled. So we're drilling a lot faster than that these days, at least to get to the reservoir. So what if we go back to the drawing board and say, why, instead of just prematurely setting casing at 7,000, why don't we drive it deeper? There's a massive shale here that has a high frac gradient and very competent rock. What if we drove 9 5/8 there to that shale? Then our next string of casing was a liner instead of a long string. We could have the short 7-inch liner here. And the beauty of a liner is, A, I don't have to buy near as much casing as I would if I was a long string. And B, now instead of running 4-inch drill pipe to surface, I can use a tapered drill string of 5-inch down to the liner top and 4-inch through the liner and out into the lateral. And that has some other really nice benefits for the things that come beyond drilling. And actually, the real reason why we're doing this is for all the stuff that comes after drilling. Our production casing can be bigger rather than having a long string of 4.5. I can have tapered 5.5 by 4.5. And when I go to clean out the frac job, I can use tapered 2 7/8 by 2 3/8 rather than a single long string of 2 3/8, which has the same drill string problems that this long string of 4-inch drill pipe has. It just wouldn't work. So here's how our VME limits look if we were to run 5-inch drill pipe on top, 4-inch drill pipe on bottom, and I do rent a little bit of 25.6 pound pipe on top. But now I've got wide margins for my expected friction factor. I've got wide margins for my torque. Everything's so much better if I've got this deep set 9 5/8 and 7-inch liner design rather than a long string of 7-inch. And this is a very real story. I didn't just concoct this. There was a group of folks that had come up with this original well design, and you start crunching the numbers, and it's like, no, there's got to be a better way. That's just not going to work mechanically. The other thing that we like to do, I mentioned this earlier, is create graphs that show the driller what's the maximum that he can pull at any point, or she can pull at any point in time as they drill the well. So this gray shaded area is what you'd show the driller and say, okay, don't pull more than this, or we're going to overload something in the string. It might be the 4-inch pipe. It might be the 5-inch 1950. It might be the 5-inch 2560. He doesn't really care. He just wants to make sure he doesn't lose his job and doesn't break something. So the engineer, this previous slide is kind of the engineer's view, and that's the driller's view. That's what you show the driller. Don't pull more than this, and everything will be okay. And on episode 1, I'd mentioned the Smart and Decker idea for NOV. NOV, this is exactly the sort of stuff that would be really super handy to just have on the weight indicator. Is if you've got a torque and drag engine running in the background and it's constantly re-updating what's the maximum that you could safely pull to before you overload something. That's the whole idea. Likewise on your torque gauge, if you've got a moving limit so that we don't overload something in the string. This red dash line now is a moving limit that tells the driller, as long as you set the stall no higher than that, you're not going to twist off something in the string. Whether it's the makeup torque as your limit or this pink shaded area is the tube limit. We've kind of intentionally designed this string so that the makeup torque is our limiting factor and not the tube. We're staying above the tube window. That's a very complicated answer to Divine's very simple question, that this should have been, just oh, it's easy. You just do the XYZ and that's how you figure out your limit. Well, it's a very complicated way to eventually arrive at what are your limiting factors. And it's not going to be the same for everybody. The guys that are drilling shallower TVD wells, the Bakken wells, for example, at 10,000 foot TVD, have different challenges than what we deal with at 16,000 feet TVD. And, at 5,000 foot TVD, it's different challenges again. So really, that's why the tools exist, is so that you can crunch the numbers on your specific case and figure out what is your biggest problem. In this case, tension is a big part of our problem. And we can easily solve it with a well-designed change. We're getting all these other benefits. We're getting a much better frac job, or we've got a much better casing run and cement job. We can actually clean out the inside of that casing after we frac it, where we didn't have the ability to do that with the original design. So that's the big picture that I hope people walk away with, is do this sort of work early enough before you order casing, so that you can come up with a design that solves the problems before they become real problems. Here's the process that you'd use, basically what we just walked through. Yep. Make sure you know what pipe you've got. Agree with the people that determine whether or not you're employed at a company, what your safety factors are going to be. I can't decide that for you, but I can tell you what's common. Use artificial tortuosity on a planned well path. Don't just assume that you're going to drill a perfect well bore. Use VME limits. Use your friction factors from offset wells. So that means you got to do a little homework and hindcast, look back at offsets and analogs, figure out what's normal in your area, and then give yourself a little bit of working margin. And everything should go pretty smoothly if you do those things. So that's the little practical exercise that I hope kind of wrapped up a lot of what we've done over the course of 2 months, and give you something that you can use going forward.
It has been 2 months.
Yeah,
8 episodes.
Wow. Covered a lot of ground.
It went by quick. Well, thank you for the presentations today, sir. We do have a handful of questions. Looks like Soren is the one asking the most today. So let's get started with them. Do they and check string for fatigue, and how, like it have done a lot of horizontal earlier?
Yeah, that's the hard part about fatigue is, so T.H. Hill actually wrote some papers, it's been a while now, about tracking fatigue cycles on a string. And this is another application of torque and drag, but the general concept is when you've got a string you're concerned about, is you keep track of where every single joint is located in the process of drilling a well. You know what the dog legs are at every point in the well. You know what RPM and trip speed and ROP you're using. So you can track the accumulated number of cycles and the amount of cyclical stress in each joint, and compare that to the endurance limit of the material that you're using. We're going to assume that we're all using steel, but the endurance limit changes depending on what materials you're using. And then if you've kept track of that for all your joints, you can come up with a very strategic way to cycle out your pipe that is starting to accumulate an excessive number of cycles. That's not what we usually do, though. And certainly rental tool companies are not doing that. They're going to rent to David today and me tomorrow. And even if I've got very good practices, tracking the accumulative fatigue on every joint of pipe, that doesn't mean David is. He's probably not. He's just happy to wear his orange glasses and do podcasts. So renting drill pipe is a dangerous proposition. And there's no inspection that you can do that will tell you that you're, near the end of the useful life. All the inspection is going to do is pick up on a crack. Once there's a crack in the tube, you're very, very close to the end of the useful life, right? It's practically too late at that point. That doesn't mean you shouldn't do inspections, but the 80% of the fatigue life has already been consumed before you start to be able to see any signs of it. So again, that's a simple question. There should be a simple answer, but it's more complicated than that. If you were a large operator, you owned your drill pipe, and you were drilling wells that induced a lot of fatigue, then it's conceivable that you could track that and be very clever and strategic about it. For the rest of us, I think it's better to just design your wells in a way where there's not a lot of bending fatigue.
Yeah, hard to keep track of like not every joint of pipe's going to have an odometer on it. And not
Well,
just the
so
odometer, then
right.
The wear and tear that goes along with that.
Yeah, you need not only the odometer, the number of revs, but you also need to know how much bending stress there was at any given point. So, you could have 500,000 revs at low bending stress and you haven't done hardly any damage. But you could have 10,000 revs at extremely high bending stress and have almost entirely consumed the life of the pipe. Weatherford had an awesome idea. They got really into RFID technology, and I don't know if they're still doing it, but when they first kind of bought into that, they were putting RFID chips in the tool joints of rental pipe with the idea that you'd scan every joint that goes in the rotary table, so you have a digital tally that that way you're not worrying about people fat finger in the tally, but also in theory, you could much more easily track what each joint has accumulated because you tie the RFID into software. The software's tracking the accumulative fatigue, and then you've got a permanent record of what each joint has experienced. So I think that's pretty interesting. Yeah, you're exactly right, Rob. You have to start with a starting point, and with rental pipe, you just never are going to start with a known.
Great comment there from Robert. All right. Next up is Russell. He says, should you consider static torque peaks for drill pipe torque limits? Isn't this difficult to model as friction factors are usually calibrated dynamically?
Yeah. Well, yes and no. So, let's say that I'm rotating along normally off bottom at 15,000 foot-pounds, and my limit, I've done the exercise that we just talked through. I've done my limit calculations, and 20,000 foot-pounds is my limit. As long as the stall is set at 20,000, I'm going to be okay. As long as I don't ever let the top of the string see 20,000, I'm all right. Now, that is going a little bit out on a limb because I'm assuming that static friction is distributed across the entire wellbore, and that might not be true. If the vast majority of my wellbore is cased, there's probably not as much static friction in the cased hole as there is in the open hole. Now, if you really think that that's a likely problem, what you could do is assign a different static friction factor to the open hole than what you have in cased hole and come up with a new limit revised on that higher static open hole friction. But boy, for the average daily user, we normally just don't go to that effort.
And Darren says, great example, Brandon. Well laid out example. We love comments here or compliments here on the show. Comments and compliments, either one. All right, I'll pull this one off. Soren asked, how much tension do you compensate for in case you go stuck?
Yeah, I should have shown this, but
you should
the
have.
longer and the more complicated the well is, the more important it is to not get stuck. Duh. But what I mean by that is as your well gets longer, the actual overpull that you can apply at the bit or the BHA, usually the area where we're getting stuck, decreases dramatically. Even if I've allowed for at surface 100,000 pounds of overpull. On that example that I just showed, that's probably going to be 15,000 pounds overpull at the bit because you lose so much of your surface tension in the dog legs that have accumulated over the course of the well. Because as you increase tension in the string, you're increasing that capstan effect that some of the other presenters had talked about. And so what you see at surface is dramatically less than what you see at the bit. Think of it kind of like it's sliding in a long well. We know that the longer your lateral is, the less your actual weight on bit is relative to your perceived surface weight on bit. You can stack out the entire weight of the drill string and you're barely drilling at all. So you know that you're not getting all that weight down there. Well, the same happens in reverse when we go to pull out. So I've become less and less interested in kind of arbitrary criteria that say you should always have 100,000 pounds of overpull margin, because really the game is don't get stuck in the first place. You should have something at surface, just kind of, and it's more just friction factor allowance. Like if you think that you're going to have a 0.2 friction factor, then I'd probably allow up to a 0.3 friction factor, unless I've done a ton of homework and I know that nowhere in this field has it ever been more than 0.25. Then okay, 0.25 maybe becomes my design criteria. But I think those, arbitrary 100,000-pound overpull thresholds are silly. They made sense for vertical wells. They don't really make sense for directional wells.
There we have it. What about checking tension along the string against the helical buckling limit of 4-inch string, specifically sliding? Are you using RSS?
Yeah. So for this application, we are planning RSS, but we also want to be able to use motors if we find that the environment is too abusive for RSS. But you could do exactly what I just showed, where you've got that roaming tension limit, but for buckling. So just slacking off instead of pulling out. The thing about buckling, and some of the presenters have touched on this, most of us are drilling with buckled pipe and we just don't realize it. And it's not catastrophic. Buckling is not the boogeyman that we kind of treat it to be in most circumstances. Most of the time, almost everybody drilling with 4-inch and 4.5 pipe has it buckled to a certain extent. The key is not buckling it so severely when we're rotary drilling that the bending stress exceeds the fatigue endurance limit. So for normal S135 drill pipe, if you can keep your bending stresses below 30,000 PSI, then Bob's your uncle. You can keep doing that for days in and days out and not damage the pipe. Now, we're super sensitive. That bending stress number when we're drilling with buckled pipe is super sensitive to the hole size. So I think that I've got a 6-inch hole. Well, what if I actually have an 8-inch hole? Because wellbore instability or whirl or for whatever reason the hole's bigger. Well, now when I rerun the bending stress calculations with buckled pipe, they're much higher than what I had originally planned. We've actually seen folks twist off their pipe because of that very issue. They drilled in an area with 30,000 pounds of weight on bid on their 4-inch drill pipe for years and years, and there was never a problem. Then they moved to a different area and they were trying to use the same mud weights, the same mud types, and it didn't inhibit the shale as well as it did in the first area. Hole grew, twisted off the pipe. Look back at the bending stress. That's exactly what was supposed to happen. Sorry, I rambled there, but you can do what I just showed. I would draw another line on there that is not just the onset of helical buckling, but what is the onset of catastrophic helical buckling. And what that means is buckling that's so severe that you start to accumulate excessive fatigue.
There we go. With more agitators and big motors, have pressure/pump limits become more concerning than torque or mechanical limits?
Absolutely, because we pump way too hard. Almost all of our pump pressure issues could be solved if we would just realize that the pump speed is a variable that we control. So here's what I mean by that. In 8.5-inch hole, we're crying if we can't pump 700 gallons a minute now these days. It was only 10, 15 years ago that we didn't have 7,500 PSI rigs and 1,600 horsepower pumps. We had to make do with 2 shitty 1,000 horsepower pumps in a 5,000 PSI system. And we were pretty satisfied with 400 to 450 gallons a minute to drill 8.5-inch hole. Now, with that said, would I rather have 600, 700 GPM to drill my 8.5-inch hole than 400 GPM? Yeah, I would rather have that. But if I'm bumping up against my standpipe pressure limits at 700 GPM, guess what? We can turn it down to 650 or 600 or 550 or 500 or whatever the flow rate needs to be in order to stay below the pressure capacity of the rig. And if I need to run dual agitators in order to overcome enough drag in order to get out there, that's fine. Do the proper planning, just like we've done on the torque and drag side, to figure out, okay, with dual agitators and 1,000 PSI diff that I want to drill with, what is the max flow rate that I can realistically achieve at TD if I'm going to add all that stuff to the string? And we get conditioned into this idea that we got to have all this flow rate, and you don't got to have it. Certainly not from a hole cleaning standpoint. Sometimes we got to have things just because we've never done it with less, or we think that we need it because we've never done it with less. It's an interesting point because what we've been seeing more and more often is we're introducing bit balling problems, even with oil-based mud, in most of the basins that we drill in, because we think that we need to have all this flow rate. We want to have all these agitators in the string, or, big powerful motors, or, 1,000, 1,200 PSI diff. And so one of the obvious things that we can take out of the system to relieve some of our surface pressure is the nozzles. We used to run, good HSI. We'd get 3 or 4 HSI and we had good bit cleaning. But as soon as it becomes inconvenient, then we open the nozzles up wide to relieve some of that pressure so that we can maintain the high flow rate. And then our bit hydraulics suck. And then we've invited bit balling. So it's an interesting little, we're chasing our tail a little bit on that front. But yeah, to Eric's point, hydraulics, I think, are a bigger issue than torque and drag for a lot of the U.S. land horizontals.
So one final comment here from Mason says, the point for buckling once sliding means challenge to transfer weight for effective sliding, low RP and poor tool face control. Hard life for DDs in practice with low efficiency.
Yeah. So the diatribe that I went on there about bending stress and how buckling's not that big of a deal in rotary mode. In sliding mode, you're right. Once you reach helical buckling, then you can't transfer weight, you can't slide, everything becomes slow and painful. One of the things to keep in mind is that most torque and drag software doesn't account for the effects of rocking. So, on these wells where when you run it out on paper and it says, you're probably going to have a lot of buckling as you get towards TD, then that's where you would want a rocking system to help alleviate some of that. Or, you start playing tricks with heavyweight drill pipe placement or stiffer drill pipe, or eventually you get to where the answer is RSS. The 3 and 4 mile laterals that people are drilling, most of them are doing them with RSS. Not to say that you can't drill a 3 mile lateral with a motor, but eventually you get to a point where it just makes sense to go RSS.
Well, there we go. No more questions. I think we
solved all the torque and drag problems.
We have reached the end of the road, and my prediction with the water hose has come true now. There is no need to watch any more about torque and drag, the Learn It, Turn It, Burn It series. Brandon, thank you so much for offering your time up to be able to educate all of us on torque and drag. Special thanks to Volant. Reach back here. So, where's it? There it is. Special thanks to Volant today. Huge shout out to them for sponsoring today's episode. As I gently put this down on my desk. Special thanks to everybody who has been watching and taking part, liking, sharing, subscribing. It makes a huge difference. And we're actually getting questions as I'm rambling on. So let's throw them up there before we get too late. Do operators take the time to do cost analysis on solutions to torque and drag, NRPs, 2 agitators, lubes, beads, drill pipe upgrades, etc.?
Yeah, sometimes when you tackle this sort of stuff early enough in the planning phase, and you've got plenty of time, then we start doing those sorts of games. But a lot of times we don't look at it until we can't turn or we can't slide, or it's in the middle of the night. You get that 4 o'clock in the afternoon phone call, and at that point it's more of just whatever I can get my hands on to make this problem go away. I'll deal with the cost. So most operators, no, I would say they don't. The ones that are planning their business well in advance, absolutely. Figure out what makes the most financial sense.
Planning ahead. At least the one thing to take away from the torque and drag mini.
It takes time, yeah, and you got to do it early.
Yeah. So Ian says, thanks, Brandon and David. Great series. Thanks to everyone. NMR says, she said, excellent sessions. Thank you, Brandon and David, for organizing such a great bunch of sessions. Robert asked a great question. Remind us how to get the slides and review episodes we've missed. Thanks for the great show. So you can watch the replays here on LinkedIn. You can watch them on YouTube. I mean, they're also there on Facebook, but I don't know who's watching there. But you can also watch them back there on my LinkedIn page. So if we go and do this little thing, if you go over there to my LinkedIn page, you can click follow, get the notification icon to be able to do that. If you scroll just past this, just down, just past, just a little bit down past, you'll be able to see there is a featured article or a featured activity of some sort that's got a link to all of the prior episodes and to the slides. We still have a couple more slides, a couple more LinkedIn posts that I need to make. We're just waiting on one person to send them over to me, and then we can keep putting them all out in order, but they will definitely be there. So I believe also on the YouTube links, I think are on the YouTube description. We're putting the links to the presentations on there as well. If not, I'll get Tracy to make sure we get that done. The Tora says, thank you guys. Great sessions. Well done. Extremely very well presented. John DeWart says, thank you. David and Brandon, great book into the series. Great series. Thanks, David and Brandon and all the other presenters. Nowfell, I got his name right. He sent me a little message. Thanks, Brandon, David, and everyone participated. Put this informative series to fun with Torque and Drag. Barry says, thanks, Brandon, David, great presentation for the series. John Young says, hashtag Volant. There you go. Today's episode brought to you by Volant. I do want to say, for everybody out there, if you guys liked this series, then do me the biggest favor possible. Like, share, click the little button. This is not possible without the engagement from the audience. And the other big thing is please let other people know in the near future. If you start having torque and drag issues, you start having questions about it, tell them to come back and watch the series. Start with episode 1 or 8. Those are the two best ones, obviously. And then finish out somewhere in the middle. Looking forward for a next show. Yeah, guys, let me know if there is a series that you guys would like for me to be able to cover next. Hydraulics, plug and abandonment, MPD, bit design, MWD, I don't know. I see it says, thank you so much for the series. Torque and drag understanding is a must for everyone involved in drilling operations. Kind of why we did it today. Thank you all, says Adrian. John Clark, it's a great job on creating quintessential torque and drag reference series. Well, we tried. And then, yeah. Oops. Well, comments are coming in pretty quick. Matthew Tell says, what's the next series? You guys tell me. Y'all tell me. Someone says, drilling optimization. Thanks for putting the, Armand says, thanks for putting this on. Already applied some of the learning. There we go.
Fantastic.
That's amazing. All right, says, thanks, David, and all the other parts. Learned a lot is an understatement to me. We've got drill string dynamics. Jorge says, thank you. Maria says, thank you. All right, we'll wrap it up there. Once again, huge thanks to Volant. Visit volantproducts.ca, please. Just go over to the website, check it out, take a look at what they've got. Add it to your arsenal of knowledge that you've learned from the Torque and Drag mini-series. Really huge thanks to them. I get to keep this and put this. It's a little tall to put on one of my shelves back there. Maybe it'll go back next to my little Lego minifigure guy right about there. We'll put it next to it. Special thanks to everybody. All the presenters. Brandon obviously could not have done this without you. 100%. You're responsible for all of this.
It was a lot of fun. Thank you.
Yeah, and one of these days I'll make it up to Montana. We'll go take a look at your little the Jimmy, the K5 project, or is it K10?
Come on up. I tell you, it's a K5. July is much better than February, just like Anchorage.
Well, one of these days I want to get up there and come see you and Brian Gallahan. And
fantastic.
Take time to visit. What is it? Big Sky?
Yes. Well, if you come in February, yes. If you're a big skier, Big Sky is fantastic.
Probably not in February. I'm not much for the cold. I'm enjoying the 80-degree weather we're going to be having here today.
You
All
and me
right.
both.
Once again, thanks Volant for being our sponsor for today. Thank you, Brandon. Thanks for everybody who's been a part. Like, share, subscribe, and as always, know your industry.